then let's look at what we want to achieve in this work here. Basically, when automotive industry, they're moving to using much higher bus voltage, also looking at using silicon carbide devices for their drive. And they start to think about, oh, if the existing installation design for the machine is good enough, like without any changing, we can directly go to like 800 volts, switching at 20 kilohertz. So that's one thing they're thinking about. And so that's why we started to think about, try to develop a high fidelity finite element model to predict the voltage stress across individual conductors or between turn to turn or between any 2 points inside the machine windings when the windings are driven by PWM voltage. And now start to talk about the finite element modeling approach we use. So at the beginning of the work, we looked at a few tools that we have. We want to take a look at which tool will be most suitable for this work. So HFSS basically doesn't have mechanical motion, and it does have integrated electric field and magnetic field calculation, but because it doesn't have mechanical motion set up, so we didn't use it. Then COMSOL and ANSYS Maxwell are very similar, but actually they don't have a real integration between electric field and magnetic field. If you want to integrate the two fields, and you still need to actually add capacitors and try to kind of integrate the effects of electric field and magnetic fields together. And then at the end, we decided to use Maxwell. It's only because it's available to us and we have been using it for a long time. Also, it's much easier to get technical support from them. And then let's look. So a lot of students, you will be very familiar with the figure on the left if you do machine design. And when you do machine design, and you can see typically you just use one bulk conductor inside one slot to represent all the wires. But if you do this, and you can accurately predict the torque production capability, back EMF, inductance. But if you want to look at the voltage stress between across one conductor or voltage stress between any two conductors, this wouldn't work very well. And so that's why we come up with the modeling on the right-hand side. And so here we have several different colors. Those several different colors represent different number of turns. And then some of you might ask, well, then when you model this, how do you know where to put all those conductors, like the position of the conductors? That's a great question. And because we actually don't know, and we actually cut open several production motors on vehicles and used some signal processing techniques to kind of figure out, okay, which several conductors are for turn one, or which, and also they're connected to which other several conductors in another slot. And then based on several motors that we cut up, and we come up with the modeling like this on the right. Okay, and then let's talk about the limitation of Maxwell if you only use a magnetic solver or electric solver. So if you work on machines, and when you use Maxwell to simulate electric field or magnetic field, you know that they're not truly coupled together. And so the problem then is, okay, if you use a magnetic solver and you can calculate things like inductance, back EMF, and torque. When you use electric solver, you can calculate electric field or capacitance, things like that. And then the problem is that, so for example, if you simulate a really simple coil like this, and so two coils in series, and then each coil has 6 turns in series, just like this, for example, using magnetic solver, and you apply a pulse voltage across these two coils. Then you look at your results, like voltage across each coil here. and it behaves exactly like a voltage divider. So the red one here is the total voltage you apply to those two coils, and then here the blue one, the black one are overlapped, and you don't see any transient. So exactly the same voltage across the two coils. Then we explored for some time. At the end, this is the approach we use. So what we did is we use electrostatic solver to calculate all the winding capacitances. So I'll talk about what the capacitance value look like. We'll look at the capacitances between every two conductors, and also capacitance between any one conductor and the stator ground wall. So we get all the capacitance values and then add all the capacitance values as capacitors and to your circuit. And then everything in the blue box here, like these things are finite element model of the coils itself in Maxwell magnetic solver. And then in this case, you apply a pulse voltage to your model again. So for example, this is the input voltage. Then you look at the voltage across the two serial coils. Then you can see all the ringing effect across the coils now. Of course, that's not enough, and we have to verify if it makes sense. Then we moved on to the next step. So next step, so if you look at last one, it's very simple, a form wound winding. You only have 6 conductors in one slot. Then we moved to a little bit more complicated case. So here we have put 16 conductors in one slot. And also in simulation, you can exactly control the position of the wires. But in test, we want to kind of exactly simulate what we have in the simulation. That's why we made a paper plate and drill all the holes in the slot and try to constrain the position of the wires. And then we measure, when we do the measurements of the capacitance, then we can compare the capacitance in the measurement exactly with the capacitances that we get from simulation. Then here we have 6 capacitance values. Those 6 capacitance values are for the capacitance between each conductor and the stator ground wall. And also we have 120 mutual capacitance values. Those are the capacitance between every 2 conductors. Then here we show the measured 16 capacitance values and the simulated capacitance values. So we use the impedance analyzer to measure the capacitance. And then you can see it has a great match between the tested and calculated capacitance. Okay, then we make it more complicated. So this one, we start to use a entire stator. And then we put 1 single phase windings in there. So for this machine, we have 2 parallel circuits for each phase. And then what you see here is only for 1 parallel circuit. And so all the 4 coils are in series. Then we have 5 turns for each coil. Then each turn has 16 parallel wires. Then if you look at the modeling on the right, then we have 3 digits to represent each conductor. The first digit means the number of turns, and the second and third digit represent the number of parallel strands. Okay, now let's take a look at the capacitance values we got from simulation. So we group them into like 3 levels, and so first level typically have really high values like these group here. So for example, let's take a look at conductor 115. So 115, okay, so they're bottom at the slot here. So if you look at the 2 conductors for this wire, both of those conductors are really close to the stator ground wall. That's why we have a high capacitance between conductor 115 and the stator ground wall. And then another example is for level 2. If you look at conductor 414, So 414 was 414. 414. Okay, here. And where's the other 414? Oh, here, okay. So these two sides of this wire, so in slot 1, it's not really close to the stator ground wall, it's kind of in the middle. But in slot 6, and it's very close to the stator ground wall. So that's why the capacitance between 414 and stator ground wall is slightly lower. Then the last group will be conductors if you look at all those conductors in the center marked by like blue color, if you look at the two sides of the wires, and both of the two sides are kind of in the middle of the slot, so it's both sides are kind of far away from the stator ground wall. That's why the capacitance values are low. And so in the simulation, we actually ignored level 3 capacitance because they're below 1 picofarad per meter. Then this page, you can see the capacitance between one wire 404, and other conductors. And we also have a few levels, but overall, the mutual capacitance between every two conductors are much lower than the capacitances between wires and stator ground wall. So for example, if you look at 403, so in both slots, you can see 403 are right next to 404. So that's why we have a high capacitance between those two conductors. And then if you look at 101, and so 101 and 404. 101. So in slot 1, 101 is kind of close to 404, but in slot 6, 101 is far away from 404. So that's why the capacitance between 404 and 101 is kind of low too. And in the simulation, we also ignored all the mutual capacitances that are lower than 1 picofarad per minute, per meter. Okay. Then the last step is to include all the three-phase windings in the FE model. The winding structure we use is on the right. So I mentioned earlier, so for each phase, we have two parallel circuits. Okay. And then before I move forward to testing, and so what we want to integrate all the capacitors with the FE model of the wire. And you can imagine if you have like 6 conductors in one slot, it's not too bad. You can do everything manually. But when you do this structure here, so each slot you have 80 conductors, you can imagine you have tens of thousands capacitors you need to add into your simulation model. That's why it really doesn't make any sense to do it manually. So that's why we use MATLAB to write code to automate the whole thing. And we can, as long as we figure out the node points, the number for each wire in the finite element model, and then what you can do is just write code, something like this. You say, oh, that's the capacitor name, and then it should be between these two nodes. And also we specify the capacitance value here. Okay, and then let's look at our test setup and all the tests we did. So for test setup, we have both single phase test and 3-phase test. So for single phase test, we just use 2 phases of a 3-phase inverter to generate square wave outputs like this. And then for 3-phase winding test, we use space vector PWM for the testing. Okay, and of course, so when we did testing, we also did a step-by-step. So step 1, if you remember, it's the similar thing as what I showed in the simulation part. And so you can see we actually have several plates, paper plates here in parallel, and put them inside the slot. It's because if you only put 2 paper plates at each side of the stator, and you might not be able to like constrain the wire position really well, especially when in the center of the slot here. But if you have several paper plates in parallel, and then you can try to make the position of the wire exactly what you want. And similar thing we did on the right hand side. So this one is the 16 conductor in one slot case. Then in the lab, in our lab, we wound this single phase random winding structure. So we have 5 turns in series, and then each turn has 16 parallel wires. The last one we did at campus is this 3-phase random winding. Then after we tested all the 4 cases, we also tested a production motor. So the difference is that if you look at everything we wound here and have really long end windings, and we don't know if the behavior of the voltage stress or voltage propagation will look the same as what we see in the production motors. So production motors and the end windings are much, much shorter. And so that's why at the end, we also tested a production motor. So of course, production motors are VPI'd. So that's why we spend a lot of time to scratch the insulation and try to find out this point is the test point we want. That point is between coil 1 and coil 2, and we spend some time on that. And then if you look at the figure here, and we get all the test points out and made this box here so we can easily access the test points we want on the production motor. Then this one is just the machine mounted on the dyno when we're doing the testing. Okay, then let's look at the test results step by step. So this step 1, we did a really simple 6 conductors in 1 slot case, and then we have 2 coils. Those 2 coils are in series, and we apply 40 volts plus minus 10 kilohertz switching frequency. And if you look at the figure here, that's 1 switching cycle. And so this is the voltage we measured across the 2 coils. And then these are the simulated and measured voltage across individual coils. And so this is a zoom in at the right front here. And so you can see we have a great match between the test and simulated voltage across each coil. So test is solid lines, simulation is dashed line. Then we moved to the more complicated case. So we just have 1 coil here, and then we have like 2 slots. In each slot we have 16 conductors. And so here you can see we try to look at when you change the position of the wires, how that's going to affect your voltage distribution or propagation or the current distribution in within those parallel circuits. Oh yeah, so sorry, I forgot. So this 16 conductor here, we did 4 circuits in parallel, and then each circuit we have 4 turns. Okay, so case 1 is a very typical random wound wire distribution. And so when workers try to put all the wires inside the slot, and you cannot exactly make sure that's all wires for turn 1 will stay all the way at the bottom like this. So this configuration here is very common. And then so case 2 is a very extreme case. Typically it's not going to happen in real world applications, because you can see that in simulation we can easily like put the first parallel branch and second parallel branch, third parallel branch, fourth parallel branch for 1 turn in position like this, but typically they will try to stay together. And the last one here, it'll give us some unbalanced voltage. I'll show results on next page, but this configuration here is also very typical winding we will have in real world, and because you can see all the parallel strands for turn 1 stay at the top, and all the parallel strands for turn 4 are sticking to the top of the slot. Okay, so this is the extreme case. So for this extreme case, if you look at the results here, if you look at the yellow line here, that's the total current in the 4 parallel branch. And then, but you can see the currents in 4 parallel branches are very unbalanced. So for example, this green one, that's the current in parallel strand 4. That actually accounts for 70% of the total current in the entire turn. And then the other 3 strands just have much lower current. And of course, this is something we definitely don't want. That's going to stress that one strand very much. But as I said, this is an extreme case. We typically don't see this case in real world application. And then case C here, it's a very typical winding for random wound case. And all the strands for turn 1 are toward the bottom. And then if you look at the voltage across each turns, and then basically the voltage across turn 1 is higher than the voltage across the others. This is mainly because for those strands, they're staying at the bottom of the slot, and you have higher inductance for those. And then, but if you look at the 4th turn, they're close to the opening of the slot, and you actually have more leakage inductance for those wires. Okay, then step 3 is the testing for the manually wound single phase winding that we did in the lab. And so we have 4 coils in series, and each coil has 5 turns in series, and also each turn has 16 parallel wires. So here you can also see this is the voltage across each individual coils, and of course it's not easy to see the details. So the one on the right shows the details for the rise front, and you can compare the voltage across each coil for both the test and simulation. So it matched very well. So in terms both of the magnitude and also the frequency for the voltage ringing. And so this is the input voltage we have. Okay, and so the thing I want to emphasize for this case is that it's actually the current uneven current distribution inside the parallel coils. You actually see a lot of circulating current. So if you look at the green curve, that's the tested total current in the 16 parallel branch. And then, so everything here, that's the individual currents in individual parallel strands. Then we can zoom in the currents in individual strands here. Okay, so here. Let me remind you, the total current looks something like this. And so after it passes 0.0 amps, and so the total current is positive, right? But you can see a lot of turns will have positive current and with some different magnitudes, and also a lot of turns will have negative current in those strands. So this means circulating current in those parallel strands. So this is very common for production motors. Okay. So next one is the testing we did for the 3-phase manually wound windings in the lab. Yeah, so you know what, when we try to wound this in the lab, and it's really difficult to try to push as many conductors inside the slot. And so for the production version, they actually have 96 conductors in the slot, but in the lab we could only put 80 conductors inside there. Also, the end windings are pretty long. And the simulation, the results here are the voltage across individual coils for both test and simulation. One, the switching status goes from 000 to 100. So that means your phase A top switch turns on, right? And so for this case, we see the highest voltage stress in the first coil of phase A. Then for phase B, C, and their voltage stress are low. Now, of course, so later we look at the switching transient, all the switching transients over one fundamental cycle. Then the so the pattern we found out is that whenever you have a phase goes from 0 to 1 or goes from 1 to 0, so the first coil of that phase will have the highest voltage stress. And if that phase goes from 0 to 1, and then the voltage overshoot of the first coil for that phase will be positive. And if that phase goes from 1, switching status goes from 1 to 0, and the first coil of that phase will have very large negative voltage overshoot. So that's the pattern we find out after we look at all the switching transients in over one fundamental cycle. Then for the production machine testing, so you can see everything is VPI'd and also the wires are bundled together. The first challenge is where if you can find out the correct test points you want. We actually scratched off a lot of insulation for a lot of wires, and then we found out all the test points we want. So those are the test points. If you get the voltage of those test points, and you can calculate the voltage across each coil. Okay. Then for the production motor, we did a lot of testing to look at the voltage propagation. So we changed the DC bus voltage. So those are very typical voltage for hybrid electric vehicle applications. And also we tried different current angles. So you know that for IPM machine, and you can control the angle between the permanent magnet and the magnetic fields of your stator. Then we also look at different current magnitudes. So we go all the way to peak current for maximum current for this machine, 500 amps. And we also did tests to measure the voltage propagation at different rotor speeds up to 12,500 RPM. And then for all the tests we did, especially for high speeds, we still used PWM for the excitation. So we didn't go into a 6-step operation region. And so when we get all the test data here, then we can compare the test data for different operating conditions. Okay, so this shows the phase A coil voltage and three-phase currents over one fundamental cycle. So we'll look at the details next. Okay. So on production motor, and we see similar patterns as what we have seen in the lab. So for example, when phase A switching status goes from 0 to 1, then we also see the first coil of phase A has the highest voltage overshoot here. And then we looked at all the data and tried to find out, okay, how DC bus voltage or speed or current magnitudes affect the voltage propagation pattern. So for example, this first one is to look at the effective phase current level. And so we have 5-phase current level here. So from 100 amps to 500 amps. And so this is for 100 amp, and then this is for 500 amps. And so actually when you have higher currents in your windings, your voltage stress across the coils will reduce. And this is also for the case when phase A switches from 0 to 1. Okay. Then this page shows the effective DC bus voltage. And so the y-axis here, we already did a normalized voltage. So it's the actual voltage across each coil divided by the DC bus voltage. And so we see slight difference. This is probably caused by caused by different dV/dt rates, because when we use lower bus voltage and you tend to have a lower dV/dt rate, then when you go to a higher bus voltage and your dV/dt rate is going to be higher, and your dV/dt rates actually will affect the switching transient behavior. And this one is to show how the wire distribution affects the voltage distribution. And this is kind of similar to what I talked about earlier, but those are much simpler case. So here we tried all different positions of the wires, and also when you look at the voltage stress across the coils, and they're also slightly different. This is mainly caused by when you have different positions of the wires, and the inductances will change. Okay, so the last one is the effect of the rotor speed on the voltage propagation. So the rotor speed doesn't have any effect on the voltage propagation. And so later we also did mass derivation to look at the transfer function of the voltage across each coil. And so the rotor speed, basically the effect from the rotor speed will be back EMF. And so our mass derivation also shows that back EMF has nothing to do with the transfer function of the voltage across each coil. Okay, so let's look at mass modeling here. So we did mass modeling for both the voltage across coils turns and also the currents in parallel wires, but I don't have enough time to cover everything here, so I will just talk about the mathematical modeling for the voltage stress across coils. So for modeling part, we started from using lumped parameter circuit model for windings, and so for example, this represents the inductance of the windings. And then so here we used a pi equivalent circuit because the shape of the circuit looks like pi. And so if we know the parameters like the capacitance and inductance resistance, and we can plug in all the values and then try to look at the transfer function of the voltage across individual coils. And then before we do that, we need to look at how the windings are connected for three phases. And so for example, for phase A, you have two types. So type 1 is like the transient between 0 states and a non-zero state. And type 2 basically is just the transients between the active states. And then you can see all the circuit connections when you go from one switching status to another switching status. And then let's look at this case. So for when we have the three phases go from 0, 0, 0 to 1, 0, 0. So that means phase A goes from 0 to 1. And then let's look at the transfer functions we got for all the four coils. So it looks pretty complicated, but doesn't matter. You just need to know the transfer functions of the voltage across each coil. They're functions of all the machine parameters, of all the winding parameters, L, C, R, and also the frequency of the voltage ringing. Then in this case, we can plot the transfer function for the voltage across the individual coils. Okay, so this is a transfer function here versus a X value here. So the X value is related to the parameters of the winding and also the frequency of the voltage ringing. So here you can see we have 3 poles here. And so the poles means that, okay, if X value hits like 1 pole, and then the transfer function, the voltage across the coil will tend to go to infinity. But the good thing is that we're not at those poles. And also another thing is that if you look at if your X value, so if this value is very large, and so that means if you pick up a window here, then you can see that the first coil voltage is much, much higher than the other voltage across coil 2, 3, 4. So this is like 2/3 of the total voltage across the entire winding here. Yeah, okay, yeah. So, and then we used our winding parameters like L and C to calculate our X value. And so it's in this region here. And also in our time domain waveform, we measure the frequency of the ringing. And so it matches this value very well. Okay, so that's all the slides I have. So in this work, we develop a high fidelity finite element model to predict the voltage propagation and also current distribution in individual conductors for inverter-driven windings. And we did experiment tests to verify the finite element model. Also, we used a mathematical model to explain the finite element model and the test results we got. So thank you very much.
All right, thank you. And the timing is great. So we now have some time for discussion.
Sure.
And I haven't seen anybody type anything into the chat box, so I'll give people a moment. But let me start with one.
Yes.
You know, you talked about random windings and positioning and so forth. Comment a little bit, I think you alluded to this, but comment a little bit on deliberate transposition. In other words, if you had some way of being specific as to where the windings are, what would you want to do?
Okay, you want to make sure, for example, if you have one wire and it goes through several slots, right? And you want it to be at different positions in different slots. So give you an example is that, I'll just directly draw it here. Let's say you have many slots here, and then you have, let's say in this slot, you want this wire to be at the top. And then in the next one, it's not 1, 2. It's probably depends on your winding pitch. Let's say 7 or 6. And then you want to put it at a different position. And in another slot, and you want to put it at another different position. So overall, the inductance of those conductors in different slots will balance out. And so we try to do this for all the wires. And then if you look at all the parallel wires, they will have very similar inductance values.
Okay, so in general, just like Litz wire and other things, you would want a given conductor to basically occupy all possible positions and give it as much
Yes.
variety as possible.
That's also what all the bar wound wave winding motors do. If students know those bar wound motors for like Chevy Volts, and so those are all like square conductors, and they will try to have one wire go like sometimes the first layer, sometimes the second layer, and sometimes like the fifth layer, sometimes the sixth layer. So that's, people already use that in production motors.
Okay, thanks.
Mm-hmm.
Other questions, either verbally or on the chat? I will watch the chat here, but anybody's welcome to ask a question.
Okay, maybe I'll ask one.
Hi, Karuba.
Uh, Hi, Julia. So just to follow up on Phil's question there, you now
Yes.
have a really nice high fidelity model to examine this whole phenomenon. So my question would be, based on the studies, are there recommendations more broadly, right? So one seems to be, populate all different places in the slot, but more generally, recommendations on either design or manufacturing, even including, do you part or don't, not to part, choice of materials that comes out of this study.
No way. Yeah. So I understand what you're asking. So one thing, it's like how we use the results of this work. So one way how we use it is to look at different winding structures. So for example, typically, if you look at the three-phase leads coming out, those three-phase leads are typically close together, but we also try to kind of distributes all the three-phase leads, not just put them really together. And maybe this phase A lead will come out from this pole, and this phase B lead will come out from the next pole. Then phase C will come out from, for example, the third or fourth pole. So in this case, we use the model to directly run it and then look at the voltage stress, for example, between two phases. And we can easily predict the voltage between two phases. Does that give us a lower voltage compared to the baseline model, or does that give us an even higher voltage stress between two phases compared to the baseline model? And the other thing we could do is, we actually did it, but I didn't include it in this presentation. So we can actually include the dielectric property of the insulation inside the slot. So for example, if you look at the model here, and so for example, at the beginning, we did all the simulation without resin filled inside the slot. And then we know, okay, what's the capacitance values will look like. And then after that, we also try to fill all the space with resin, or try to fill it, for example, 40% filled or 80% filled. Uh, for those cases, we can also look at how the capacitances change when the capacitance change, and we can also look at the voltage stress. So the typical pattern is that when you have resin inside the slot, inside the space here, the more resin you have and the higher the capacitance values you have for both the mutual capacitances between every two conductors or capacitance between conductor and stator ground wall. And when we have higher capacitance, and basically you can either, so before we did all the mathematical modeling and we had to run the simulation and see how the voltage stress look like. But after we did the mathematical modeling, and we can quickly use the transfer function to take a look at the voltage stress. So that's the second application. We can use the results of this work.
Good. Maybe I'll ask one pointed question. What
Mm-hmm.
would you do different in the next motor you build based on what you observed here? I mean, you brought up a good point about this capacitance, right? That
Uh-huh.
so we like to impregnate the windings, but I guess you're pointing out that that can actually make your capacitance higher, which may or may not be. I guess for me, still a good thing because all right, it's higher, and maybe the first turn sees a elevated voltage, but maybe the potted coil is more tolerant of stresses. So I can imagine it leads to a lot of follow-on questions like what are the right trade-offs? And maybe that's what you're seeing, that there's no one simple answer. I'm just
Yeah.
curious. Yeah.
Yes, sure. And so I guess so automotive industry, and the first thing we'll try to do is to see, okay, when we go to a higher voltage, or when we move to higher switching frequency or higher DVDT, is the existing design still okay not to have excessive voltage stress? And if it's okay, they wouldn't try to modify the entire design. But if they see, okay, so from the simulation or analysis, you see, oh yeah, the voltage stress kind of it gets close to the partial discharge inception voltage, then they will start to think about, do we need to like have a big change to the current design? And so like you said, the insulation material that we fill in the slots, it has pros and cons. So if you have higher dielectric strength, that's actually going to increase your voltage stress, but actually it also provides a better protection in terms of insulation. So I guess we can look at it in this way, because we have this modeling approach here. Then we can easily use it to predict the voltage stress when they have a new design, and see if that new design meets their insulation design requirement. But if you ask me how they're going to improve their design, I don't think they will try to do a lot of changes if they don't see the voltage stress will increase a lot for silicon carbide devices or moving to 800 volts.
Got it. Thanks. Good
All right,
work.
thanks.
Sure.
We have time for, I think, probably at least one more question. We will certainly wrap up well before the hour. But anybody else? If you don't, I do have one more.
Can I ask one question?
Yeah,
I was
please go
hoping
ahead.
that students will ask, so I wanted to give some time.
Yeah.
If there is okay. So Julia, again, thanks for the presentation. I think it's a lot
Sure.
of work in making sure those windings stay at their spot. I think that's spectacular how you guys did that, keeping the windings together. I'm still
Yeah.
trying to wrap my head around that slide 13. If you can go to slide 13. It was very interesting slide because I was trying to understand the physics behind this, understanding how the capacitance, and help me here if you can a little bit in terms of when you say it's close to the ground wall insulation, basically the core is grounded. Is that correct?
Yeah, the stator is grounded.
Yeah, so if I say that way, then I was wondering why only the bottom one is 115, 114. If I look at slot 6, that's where I have maximum capacitance. But my other windings, which are like, say, for example, 512 and 505, aren't they close to the ground wall as well?
Okay, so five which?
Sorry, slot 6. Let's go to the right next figure.
Okay.
Yeah, 512 and 5, exactly there, 512 and 505, where your pointers are, just a little bit below.
512.
Yeah, and 505.
Okay. So the 512 are also really close to ground wall, but the problem is that they're close to the slot opening. And so when they're close to the slot opening, they will have a higher leakage inductance. Oh, sorry. Yeah, sorry, it's not inductance, it's capacitance. Yeah, it's because they're kind of close to the slot opening, and so when you look at the electric fields distribution using electrostatic solver, and so toward the bottom of the slot, and you will see higher electric fields compare looking at these two conductors when they're kind of closer to the slot opening. And it's also because of this material difference here.
Okay, okay. Maybe I need to think a little bit because I picked an example because if I look at again slot 6 and some of these green colored conductors, they are also very in the bottom. It's like yeah, it's a little bit difficult for me to wrap my head around saying that what's the difference between say for example exactly 1112 or even 205. 205 is very close to the ground wall insulation, but and also it's very close to 114. So 205 in slot 6. Yeah, exactly. Yeah, exactly.
205. Okay, where's 205 in the other one? 205 in the other one.
Yeah,
Oh, it's
that's
here.
yeah, exactly there.
Okay,
Yep,
here.
yep.
Yeah. So these two are actually similar. I mean, 112 and 205 are similar because, so 112, this conductor is close to the ground wall. And then this 112, you have one in between. So this 205 in slot 6 is right next to the ground wall. And then 205 in here, and you have one conductor in between 205 and the ground wall.
Okay. Maybe I need to look at this picture for a longer duration. I need to stay here at this. But this is very interesting to see how the capacitance changes because of the location. So I think thanks for the answer.
Yeah, sure, no problem.
Okay, well, at this point, we really are out of time. So I really appreciate you presenting this. This is a great seminar, and I hope that we can get you to come and visit when we're able to get back together in person, and look
Yeah,
forward to it.
definitely. Yeah,
All right.
definitely. Yeah, thank you
Sorry,
for
Phil.
this opportunity.
All right. And you have a
And
good
I
evening.
think it was
Else?
recorded.
It was recorded.
Some of it was recorded.
Most of it. Yeah.
Okay.
So hopefully we'll be able to work that out. All right.
Okay, I'll send the
Thank you,
slides to
Julia.
Robin. Yeah, sure.
Okay.
And then
Perfect.
Robin can share it with everyone.
Excellent.
Okay.
Thank you,
All
Julia.
right.
Very interesting work.
Yeah,
Thanks.
thank you.
Thanks, everybody.
Okay. Yeah, bye, Pete.
Yep.
Bye, Phil.
Bye,
Karuba.
Julia.
Yeah, bye, Arjit. And bye,
Bye,
students.
Julian.